guys hear me in the back, or do you need a microphone? What? You want a microphone? Okay. I can't hear you. Hi everyone. I'm sorry Ed's not here. Not that I'm sorry that you are here. So. I know everyone came here because they thought Ed was going to be here and he's not, so let's just get on past it and move on. So if you haven't, actually raise your hand if this is your first HSC conference. Wow. Oh, that's so awesome. Wow. I just told somebody I can tell all the same jokes again. I don't actually have any funny jokes, but you'll laugh because it's your first time. We started this, actually Ray Truman started this in PEI. Ray is in the back there. And many years ago at PEI, we had an idea of there was lots of questions about science and clinical drug development stuff from people, and there wasn't really a venue for people to ask those questions because the program was really packed. And so Ray had this great idea of let's just go sit down in the pub, this is PEI, and just be like, hey, what's your questions? And he roped me into helping him, and we did it, and we were there for ages, and it was fun, and people asked tons of questions, and we realized we don't really need a program that you guys have questions, and this is a good time to answer them. So Ed and I have done this a couple times, and Ed's gone, and the much lovelier and probably smarter Tam is here to help us go. So without further ado, I didn't say that word. Anyway, what do you want? What's your questions? Science questions, drug questions, hair questions. Guess I just got a cut. Yeah, over there.
Just wondering, the ASO approach drug, seems so promising. Broad access to drug.
Sorry, can we do a mic maybe for questions? Sorry, it's a big room. Sorry.
Any idea when the ASO Roche pharmaceuticals drug shows a lot of promise, and what make broad access drug see? How far out is it? Also, things like costs and costs to administer the drugs. I think it has to be delivered in spinal fluid.
Yeah. So a couple questions around the development of a drug called an ASO drug. We broke this down last time. Do you want me to draw and you can talk for a minute?
Okay, just so everybody's on the same page about the ASO strategy. This is a Huntington lowering strategy. So the idea is that we know the cause of HD is inheriting the HD gene. The HD gene codes for the Huntington protein. And there's something about the expanded Huntington protein that is toxic to our brain cells. And so the idea is, if we can reduce the amount of this toxic Huntington protein, that's a good idea, as a treatment for HD. Now, the way that we can do this, it's actually a super, super cool technology. This has been in the works for decades, trying to figure out how to use this super cool technology. How this works is that we have the HD gene, which is made of DNA. A copy of that DNA is made, which looks a lot like DNA. And this is RNA, it's called the message. The RNA is translated into protein. So the concept is, if we can stop this at the RNA stage, we won't get the toxic Huntington protein developed.
Favorite colors.
All right, excellent. So the technology that was developed is that there's actually a way to knock down this RNA by building a tiny little piece of DNA that looks just like the Huntington RNA message. And when our cells see this kind of thing, when they see an RNA bound to this little bit of DNA, they basically say, okay, this does not belong here. This looks a lot like a virus. Let's get rid of it. And the cell has mechanisms to shut it down, integrate it, and then the protein. Yes, Pac-Man. Pac-Man. That's exactly what it looks like in the cell. Eat up the RNA, and then no protein is produced. Okay, so that's the strategy of the drug. It took a very, very long time to get to the point where we could actually put these little bits of DNA into people. And it's not easy. It has to be done through a spinal injection. Yeah, lumbar puncture. The question was, when are we going to have this drug? That's your question, right? Tomorrow.
Yeah, if you look in your swag bags, you'll find a little bit. You can have some. Just kidding. Everybody just starts like putting. No. So the question. So the drug. Well, it's not a drug yet because we don't know if it works. So when you do this approach in animal models, right? You take a mouse or a sheep or a rat. Any other? Did I miss any other species? Fruit flies. If you make an animal sick with a mutant HD gene and then give them these kinds of ASO type drugs, they get better. So the concept makes sense. It's been highly validated in the lab, but mice are not people. And so we have to prove that it works in people before anybody gets access to it. And what's happened already, which you can read about on HDBuzz, is a series of successful experiments in the clinic, including a recent safety study, a so-called phase 1 study, meaning just like a study to see in 46 or 48, 40-ish people, whether the drug, when given monthly in spinal fluid injections, was safe. And it was shown to be safe, which was really exciting. And there was some other lab-based tests that were done that suggested that it was doing its job, and that levels of this protein were going down in the only thing we can measure, which is the spinal fluid from people, because they don't like it when you ask for a brain tissue donation. You can do it, but you're never the same afterwards. So we can't take a chunk of their brain tissue and measure it, right? But what we can do is take their spinal fluid, and you can actually see the Huntington protein in there. Actually, Dr. Weil, among a lot of other people, was part of that work. And so they could get the people that got the ASOs through the spinal fluid had levels of the Huntington protein go down. Amazing, exciting, cool stuff. So all that proves that the drug is safe, and it probably does in human brains what it does in animal brains. Huge advances, but doesn't tell us anything about whether the drug works. That trial, a safety trial by design, has a tiny number of people in it, because you're taking a molecule that was conceived by people and you're putting it in the spinal fluid of living human beings. Like, that's inherently dangerous. Like, as many safety studies as you do in monkeys or whatever, you don't know what's going to happen. And so that's why safety studies are small. They're just large enough that you get it. That, if there's going to be a really bad effect in a subset of people, you'll see it, but it's low enough numbers that you're not exposing people to risk that they, more than you have to. So that's why safety studies are short, intense, and very, very carefully observed. And that's what's done. What's not done is seeing if it works, and for that you don't need 40 whatever people, you need 600 and whatever people. And the trial design that was announced by Roche in September, who is the company that's going to be conducting this trial, is I think 660 people. It's a lot. And those people are going to get drugged for around 2 years. They're going to get observed very carefully, and so that has to happen before anybody has access to the drug, because that's the only thing that's going to prove to us if the drug works or not. So for this particular drug, this particular program, that's the timeline. So I think, this is just Jeff talking, I don't represent either of these companies, but from what I understand, they're hoping to start the trial formally like next month, January kind of time frame, very, very imminently, and start enrolling people as soon as they can. So you can do the math that, not everybody starts the trial on day one, like there's a stagger, right? It takes a while to get people into all the sites. So it will take a couple years to run this trial, and there'll be, hopefully exciting advances along the way, but it's a few years from us knowing whether it's going to be a drug or not at all. If it is, the question of how much it costs, above my pay grade.
No idea.
There's folks here from Roche, and I would encourage maybe another format for that discussion. These drugs are complicated to design. I've been working with Ionis, the company that initially developed this drug, on this program for like 10 years, and nobody was getting paid during those 10 years. And so all the people working on it have to recoup that costs, and the consequence of that is these rare disease drugs tend to be very expensive. Now, you guys live in a civilized country. And if this drug, changes the course of Huntington's disease, which is what we all hope, what's going to happen is the companies are going to work with Health Canada and the provincial, authorities, and they're going to come up with a system, and they're going to say, hey guys, look, this is expensive, but it's cheaper than HD patients. And the government, because they're brilliant, are going to say, yes, you're right. Where do I sign the check? The end. Yeah. Okay.
Do we have a mic? Yes, please.
We need a mic runner.
count is 42. I have 2 grown children. Can you please explain to me gene silencing in layman's terms?
Gene silencing, you want to do it?
Gene silencing
And the difference
In
between
layman's terms.
in layman's terms. Are we talking like CRISPR gene silencing or Huntington?
No, I think just Huntington lowering.
Huntington lowering. Okay, we need to distinguish between gene silencing and Huntington lowering, because those are, the goal is the same, and which is to reduce the amount of toxic Huntington protein, but they're not exactly the same thing. So gene silencing, can we go back to the DNA RNA?
I was trying.
I know. It's a good job too, sorry. Welcome back. So gene silencing involves actually changing things at the level of DNA. We can't do that. Scientists can do it to like cells in a dish or animals, mice and stuff like that. We actually know how to do that. You've probably heard of CRISPR technology. But that is not something that is anywhere close to happening, to treat brain diseases in humans. The idea of Huntington lowering, and just getting rid of or at least lowering the amount of RNA so that we have less protein, is a much more feasible and makes a lot more sense. The thing is, we might not need to get rid of all of the Huntington entirely to see a benefit in symptoms. And so the idea of doing something that we can modulate and also be able to turn it off if we need to is a much better strategy. So I don't know if I answered your question. Basically, it asked me to explain gene silencing in layman's terms, right? We can, it's like semantics. It's hard to turn off a gene, but it is possible to lower the amount of the gene, the product of the gene, which is the toxic Huntington protein. Does that make sense?
Yeah, I was just going to add a historical note. Like, when ASOs and other drugs like them first came out, we used the word gene silencing. Lots of people did. I did. Lots of people said it that way. And really, it's not right. As Cam said, those techniques don't lower it all the way to zero. That's what silencing means. It means like turning all the way off. And so people started getting confused and worried that we were going to completely shut things off. And so it's just like she says, it's a semantic thing. We've been trying to say like Huntington lowering, because that's what we're trying to do, is lower levels of that bad protein. So yeah, just trying to be a little bit more accurate in the way we talk about it. In the front row.
So related to that, what about the good Huntington protein? And what happens if you were to lower it so much and then the person body doesn't have it anymore?
Good segue, person in the front row that I totally didn't pay to ask that question.
We'll order a drink tonight.
Drinks are on HSC. Have tons of money. So that's a great question. So let me unpack that question a little bit, because you're obviously very smart about this stuff for people who it's their first time. So the question was about so-called wild-type Huntington. And wild-type just means it's like what you say in genetics about, like, you're not supposed to say normal, because it's not nice to refer people as mutants or normal. I'm a mutant, so I can say it. It doesn't matter. It's the normal copy, right? So everybody inherits 2 Huntington genes unless there's something really weird in your DNA. What do you want to draw on?
Sure.
So you got a Huntington gene from mom and a Huntington gene from dad. If you're a Huntington patient or destined to become one, you have 1 mutant copy of the HD gene that you got from your sick parent, and 1 normal copy, the so-called wild-type copy that you got from your other parent. And only, as far as we know, only the mutant copy causes everything bad we know about HD. So the normal copy is just a bystander. It doesn't really have anything to do with the disease process as far as we know. So really, we don't need to target that copy to make HD better, in theory. And there's some evidence that that gene, the Huntington gene itself, has really important roles in the brain. We know that from animal experiments, where if we completely get rid of Huntington, which is not what these drugs do, that weird things happen in the brains of animals. So there's something this gene does that's important for healthy brains. So there's another approach. Next time. So there's another approach of. So let me back up. The Roche Ionis trial that we mentioned uses an ASO, a drug that recognizes both the normal copy and the mutated copy. So it lowers both of them. It doesn't lower them on the order of like 75% or something. And as far as we know, that's healthy. It's been tested in not just rats, but like primates and like really sensitive safety studies. But again, people aren't humans, and there might be things that come out that are concerning, in which case there's another company called Wave Life Sciences. They have people here as well. And they have not one, but 2 trials ongoing for another ASO that targets just the mutant version of the HD gene, and not, of the RNA actually, but not the wild type or the normal copy. And so in theory, that's a sort of cleaner approach, right? It's in theory better to just get rid of the mutant gene and leave the other one alone. So you might ask, well, why not just do that? The downside is that not everybody's eligible for that study. You have to not only have a mutant HD gene, you have to have another little genetic variation in your HD gene that is associated with the expanded gene, and about a SNP. I'll let you explain SNPs in a second, because that doesn't sound fun. The way drugs target these other little tiny genetic variations that Tam will explain to you in a second, that are on your HD gene but aren't the long CAG expansion, right, the mutation that causes HD. And by targeting those, Wave is able to make only the mutant copy go down, but you have to have the right variant. And so the first part of being part of that study is you have to go and have your DNA tested, and if you don't have the right variant, their drug won't work in you. And so the first drug they're testing will work in about half of HD patients, and the second drug they're testing, it's why they're testing more than one, would work in about half of the remaining people. So you'll realize that still leaves a little bit of people that aren't covered, and they have plans for doing additional development. But the idea is it's a more targeted approach, but the downside is that it's not everyone is eligible. So that's the trade-off. Small editorial point. It's amazing that more than one company is testing Huntington-lowering drugs like at the same time. Both of these companies know about each other. I'm sure they would all like to win. But they're both like, okay, great. If one turns out to be safer or better, and then we know, and then that one gets licensed, and that's what happens. This is how this goes. And it's incredible that we went from like, nobody really cares about HD to like companies are competing now to have the first Huntington-lowering drug, and that's super exciting.
Okay, who wants to know about SNPs?
I do.
Okay, I'll try to make it as quick as possible. But basically, like Jeff said, we get one copy of the gene from mom, one from dad. Most of the gene from mom and dad is pretty much the same. The only difference is, so we're working with dad had HD and he had a CAG expansion in his gene. So the CAG bit, those CAGs, those are 3 of the 4 different kinds of bases that make up DNA. There's also a T. They come together in different sequences, and the sequence is really important. If we have too many of these CAG bits in our Huntington gene, that's what causes HD, because it leads to an expanded protein. If we could just target the CAG part, that would be great. But the thing is that the CAG bit exists in this gene, it exists in the normal gene, and it also exists in other genes that just happen to have a CAG bit. So we can't just knock that down, because we'll be knocking down other proteins that we probably need. So what we do instead, and this is the strategy that Wave is using, is they look for bits of the protein that aren't exactly the same. So the parts of bits of the gene that aren't exactly the same. The parts of the gene that are really important are always going to be exactly the same in everybody. But there are other regions of the gene that aren't as crucial, and they have slight differences. So this gene might have a T in this position, and this one might have an A in this position. And what they found is that a lot of times the A in this position is attached physically to the gene that has the extra CAGs, the gene that causes HD. And if it's an A here, usually, and if it's a T in the normal gene, we can actually build ASOs against that little difference. Yeah, we don't want to knock down the normal one and leave the mutant one, that would be really bad. So yeah, basically, if you have an A in this position, which is attached to your expanded Huntington gene, then you would be eligible for the Wave drug. And if you don't, then we gotta hope that the Roche drug works. Does that explain SNPs? Yes? Okay. We have a question over here.
How are those drugs administered? Are they also able to
Same.
Yes, same. Yeah. These little bits of DNA would never make it through our system. They wouldn't get past the blood-brain barrier, and so you have to get them in there a different way, and the spinal fluid is the way.
I'll take this question in a second. I want to say something. There's sometimes people think that only the most recent thing is the only thing that's going on. There's a ton of other stuff happening at different levels, and one of the in September in Vienna at the European Huntington Disease Network, another company called PTC Therapeutics showed data from animals, from a mouse, not from a human. And they have a really weird drug that I don't, if you told me how it worked, I would have said I don't believe that's possible. But they showed data where they gave mice this drug in the drinking water, which is the equivalent of like us taking a pill, and levels of the Huntington protein in their brain went down by about like 80%. So in animals, crazy mechanism that, you know, who knows if it's going to carry all the way through into human studies, but just to say that like these ASOs are not the last thing, right? There's already another potential way of changing levels of Huntington in the brain. And PTC, I don't obviously speak for them, but they said in that presentation, they said that they were going to aim to be in humans in the clinic in the year 2020. So not very far from now, assuming everything goes right between now and then. Yeah, oh yes, front row, sorry.
Okay. Right. So.
Did you get corrected by a real doctor?
Yeah, I got corrected by a real doctor, and what he told me to tell you though, I have no idea. Stereo, let's let him do it.
So people have asked the question, how do we get this stuff into the brain? Well, the current studies are people in the front row here sticking needles in your back and putting the fluid, which contains medication, into the fluid that surrounds the brain. And that's good because it's a fairly easy approach. And these drugs have a certain life in your system. And if they don't work, they're going to go away. There's another approach where you can put these medications in viruses, and then you stick a special introducer into the brain, and you introduce the virus that contains the antisense component, and it spreads to different parts of the brain. But when it's there, and you can't get it out. So I don't know if I want to be the first on the block to have a single shot injection to see if this works, because if it doesn't, we're in trouble. However, this is going to start to happen in Poland later this year. And there's another kind of thing, corrections here, that is affecting the DNA directly, called single finger approach, where there's this thing that sort of snips out some bad DNA and sort of splices the other DNA together, which is sort of a technology before the CRISPR really started. And that's going into people later this year too. Nowhere near.
So lots happen.
Thanks, Dr. Gutman. And for the record, Dr. Gutman signaled to me to talk about that was. So you guys tell me what it's doing. All right, from the question.
Here, why don't you just.
I have one follow-up question for Dr. Gutman. Is the zinc finger trial specifically for Huntington's patients?
Yes.
Oh, Huntington?
Wow. It's not
total.
Okay.
We didn't hear that.
Sorry, we're trying to differentiate medication that could lower both the good and the bad copy, the mutant and the wild type, versus just the mutant. So this zinc finger approach, from what I understand, goes to both. And the first company that's doing the stereotactic injection is for both.
Not to correct the correction of the correction. Actually, the zinc finger binds to the CAG, so that it's actually CAG targeted. So if it works as it's designed, it would be allele specific and target the mutant. And technically, there's a couple of zinc finger approaches. It can either just bind to it and block making the RNA, or it can actually cleave as an enzyme and chop out the CAG, both of which are in development. But the one that's coming, that could come into clinical trials first, is a blocker that blocks.
Dr. Raymond, did you want to correct the correction of the correction? Good.
I know Dr. Rowan is doing a presentation tomorrow, so I don't want to steal his thunder, but I'm just wondering when we might get an update on the results of but in terms of like results or findings, what are the timelines for the study? And I'm also curious about the timelines for the Roche study. I know it's going to phase 3 and it might be starting early next year, but if you could just let everyone know how long that study might be and when we might see some results from that as well.
Wait an hour. Mid next year for the high-level results, which, to put things in perspective, the whole INS Roche project had those results a year ago. So there are different phases of different projects, but it's exciting that both of them.
Okay, does anyone have a question that's not about ASO timelines? Yes. I don't know why I'm being grumpy about ASO timelines. It's super exciting. Just one.
Hello. So this is my first national conference, and I do have a question, but I just wanted to take the opportunity to say, when I signed up for this session, and it was called Ask the Scientist, the thing that really struck me is we have scientists to ask. So I sometimes imagine you feel like maybe there's a lot of people you're carrying on your back, but I just want to say that our community has the utmost respect, and we offer you so many things for your choice to join us. Jack, you're stuck with us. But the fact that we have neurologists and scientists and research assistants and pharmaceutical companies and people helping us reach that finish line, it means so much. So there it is.
No, I'm kidding. That's wonderful. And I'll have to tell you, like, I interact with a lot of these people, I do a lot of this, and, the companies get, they come into this disease, they don't actually know HD families, and they quickly get to interact with folks, and it's mutual, and I can tell you a lot of people care a lot about this, and even the people that don't come from an HD family that work on this, by the time they work on it for a while, they get to know families, and nobody's going anywhere until the problem sits. So you had a question about science?
Okay, so I have a question. So I know we never want to bet on one horse per se, and there's a lot in the media world very, very excited about gene silencing type of drug. From your perspective, is there anything other than, we've already covered a few different areas, but is there something really exciting and really new that hasn't reached us in terms of the HD community yet?
Yes, absolutely. I'd be happy to start with this stuff, because some of it is what we're working on in the Trail Lab. There was a really big study that came out a couple of years ago. It's a very important study. It's called GWAS, or Genome-Wide Association Study. And this study was asking, we know that some people who get HD get sick early in life, and some people get sick later in life, right? We know that the CAG expansion is what causes HD, and the longer the expansion in general, the earlier people get sick and the worse that their symptoms might be. But there's a lot of variability there. So somebody that has, so somebody that has, say, 42 CAG repeats, on average, they might get sick at this age, but there are people who get sick when they're in their 30s that have 42 repeats, and there are people that get sick in their 60s. So the question is, what is the difference between these people? Like, what is the magic thing that's causing somebody to get stay healthy until their 60s? And the way that they did this was they looked at a lot of the other genes in the body and just asked which ones are different in the people who get sick early versus the people who get sick late. And what they found was that a lot of these genes, a lot of these genes have to do with DNA repair and basically managing oxidant systems in our, if you've heard of those antioxidants, we like antioxidants because they fight against oxidants. Oxidants cause damage in cells and they damage DNA, so it's kind of all related. DNA repair is really important in HD. This is what we know. We know we can count on this information because it came from a huge number of people, and it came from people, not mice. It came from HD patients, and a lot of them. So we know it's relevant to HD patients. And it started at, like, they analyzed like 4,000 people at the start, but it's up to, what did you, 14,000?
Thousands more.
Thousands more people have been basically looked at all our other genes, and we get the same answer again and again. DNA repair genes, which we have a lot of DNA repair genes because we need to make sure our DNA, those blueprints for all of our proteins, we've got to make sure that they're in good repair. What that means is that it means a couple of things. For one, it means there are other targets besides Huntington. Obviously, the best, we're such a good team. Obviously, the best target is going to be the Huntington protein itself. We know that's what causes HD. If we can knock that down, we're in good hands. But if for whatever reason that doesn't work out, maybe it doesn't, maybe the drug doesn't work how we hope it would work. Maybe it turns out to be not accessible to everybody. For whatever reason, we don't want to put all our money on one horse. And this is a really exciting opportunity because DNA repair genes, if we can tweak them one way or another with other drugs, if we can put disease off by 30 years, I consider that a treatment. So, Tammy's so excited. So, and the good news too, and I'm like, I've been thinking about this because I'm going to say all this stuff again tomorrow, so whoever comes to our session tomorrow is going to hear the same story. But the good news is that these DNA repair genes and the proteins that they code for, they've been targeted by drugs a lot already in the cancer research field. Now in cancer, the goal is to mess up the DNA repair machinery and kill the tumor cells. And that is the opposite of what we want to do. So we're obviously not going to be able to use the drugs the same way. But the fact is that there are a lot of drugs out there. We know a lot of information about these DNA repair proteins. And so we may be able to tweak them. And that is another strong strategy for therapy. Do you have any other ones?
Yeah, no, that was going to be mine. And that, I want to say a couple things about that just like at a higher level. One is that the DNA for that study came from databases of people that some of the cases was decades old. Like some of those people probably had passed away, right? And they didn't know that this technology was going to get invented that would let this happen. They just said, use my DNA, use it for research, good luck. And so that's really the power of these like huge databases of people. And it's why being in some of the enroll studies, why we always talk about it. Because it's incredibly important to have people you have DNA for and that you know stuff like what was your CAG size and when did you get sick. And then you can do now these technologies get developed that we've never dreamed of that let us ask these questions. So to me, these are the most exciting things. And the other thing to take from it, again, kind of at a higher level, is that you never have to ask yourself anymore if it's possible to delay HD, because it is. There are people that have some weird variation in some DNA gene, and they get HD way later than they should, years in many cases later than they should. So it's, as the geneticists say, nature has already done the experiment, right? The data is there. It's possible to make HD be years later because there are humans out there in which that's happening. Now, it's tricky. We can't use that to go change people's DNA to match theirs yet, but we can develop drugs that basically mimic it, and drug companies are really good at developing drugs to do stuff like that. So it's another really exciting future possibility for treatments.
So I know about clinical trials and inclusion and exclusion criteria. I actually worked for research ethics board at Children's Hospital years ago, so I'm not medically trained, but I learned from work in that. So I guess my question is, when they're making these new trials, are they going to be targeting the younger people who are gene positive and hope to stop it from there? Or, like, my husband is 62, will he be able to enroll? And I know you can't answer all the inclusion, but I want to know, is it possible for somebody older with the disease to have it, somebody younger? Like, will they include a lot of people? That's
Good question.
Yeah, that's a great question. So the inclusion-exclusion criteria for the Roche trial are public. So if you go to HDBuzz and you look at one of our last stories about, there's a link to their slides, you can just see them. And I'm always careful about saying them exactly because I don't know anything. I can fix your mouse, but I cannot answer those kind of questions. But there are inclusion/exclusion. I think it's 25 to 65, Laura, for the Roche trial, and so there is an age range. And there's furthermore, there's something called a CAP score. And a CAP score, it's just a mathematical way of combining your age and your CAG size. And what they found, and again, this is from studies like PREDICT and other observational studies that we all participated in, they found that like the trial is much more powerful if they limit the people in it to people that are like getting worse really fast. Like there's a very, what you don't want to test drugs in somebody whose symptoms are kind of flat, like somebody who's, in very late stage diseases and they're not changing very much. The easiest way to see if a drug is working is to give it to people who are really going through that first kind of like steep period of decline when things go bad pretty fast. Because when things are changing, it's possible to see if you're making them better, right? And so they're trying to limit the people a little bit to being people where they can see it change. And so that's where things like these age ranges and the CAP scores come in. So for the Huntington lowering trials, to back up on the age thing the other way, there's a lower limit of 25 because one of the things we know about Huntington is it's important in the developing brain. And your brain is not done developing when you're born. Your brain isn't done developing until your early 20s. And so lowering Huntington in the brains of people below the age of 25 might be a bad idea in a way that it's not bad for older adults, if that makes sense. So specifically for the Huntington lowering trials, that's a justification of lowering. And it's a big consideration for juvenile HD. And I know that's people's concern. And I know people have talked, these companies know about juvenile HD and they're aware of it. And it's something that's a very tricky problem. I don't know what their answer is going to be, but it's not easy on the other side. The other thing is that, and I go through this myself, I have already started looking at the inclusion/exclusion criteria to think about my own family, wanting to call friends or whatever, and there's nothing you can do. It's why we have these inclusion/exclusion criteria, because it was figured out ahead of time to be the exact right population to answer the question as quickly as possible. And one thing I have to tell myself all the time is trials are not treatment. This drug trial is not designed to treat the people that are in it. It's designed to tell everyone whether the drug works or not. The best way for us to get that answer fast is to run the best, most efficient trial, and the brains that be have determined that this, including and excluding this group of people, is the quickest way to get that answer. So I think I get angsty about it too, and I totally know where everyone's coming from, but that's why these decisions are made. So did that help?
Yeah, but I think what I see from our community as well, younger people who have the onset earlier, like the movement Korea and that. And then you see, I'll just use my husband as an example, which is easy. He has minor Korea, wiggles and jiggles and wobbly wobblies, and mental health issues more than dystonia and that. So you would have seen him today, and you could see that. So we're willing to get into a trial to help the disease because we don't have children, so we're not passing it on. But if we can help other people, that's what we want to do. So kind of we still want to be included. We still want to be included to help. So.
One last thing about that, and you guys, the real doctors in the front row can correct me if I'm wrong, but the outcome measure for the Roche trial is TFC, right? No?
In the States.
In the States, it's TFC.
And it's something else in Europe?
So there are the endpoints take into consideration other aspects besides movement. Okay, and you asked about pre-symptomatic trials. I'll stop in just a second. I want pre-symptomatic trials. I want people to get a drug and not have HD rather than get HD and try to get better. Everyone wants that. No one has any idea how to make that happen. There's lots of ideas. Nobody has a plan, I think, for now on how to do that. Because think about it. Okay, you take a couple hundred people that don't yet have HD, people like me that have a mutation and aren't sick yet, and you give them the drug every month, and then you wait. And then you wait. And then you wait. How long do you wait before you say, okay, he didn't get the disease, not because he didn't onset yet, but because of this drug?
Economically, that would make sense.
Right. Who's paying for the drug in all those years? And so it's not, I shouldn't make this sound impossible. There's probably really smart ways to do this. And the FDA has convened a working group just on this problem. Smart people are thinking really hard about it, but it's a very tricky question.
Just to continue on that point, once we do find a drug that works in that little population, we're not going to just stop there, right? So then we'll be able to tell, okay, and we'll be able to see if that drug works in pre-symptomatic people. That will come. But we first have to find a drug that slows progression.
Other questions?
Sure. You were talking about some of the proteins that are possibly linked to later onset.
Yes.
And maybe knocking that out, and there's all the drugs already for cancer and things like that. I'm presuming that you would need to use the spinal tap to administer them, which would be way cheaper and probably a lot safer too. Is that logical?
That is definitely logical. So we're really excited about the plethora of targets that GWAS uncovered for us. But the truth is, we don't know exactly, well, we have a couple ideas of a couple of proteins that really make a big difference, but we don't know exactly which things to target just yet. So we won't know until we know exactly which ones to target. We won't know how to administer the drug and things. But it is more likely that if the drugs exist, they're probably bioavailable drugs. They're probably drugs that you can take in a pill form. So it makes sense to search through the ones that already exist. They've already been through safety trials. Search through those and see if there's something that we could use too. Is a better strategy, and that's how I see it going down.
There's a question in the second round.
Yes.
Yeah, related to the GWAS studies, is there any data on, like, if you don't have a large number of categories and your onset of symptoms is quite late, do you have any data on the progression of Huntington's?
So, are you asking basically, like, if your CAG repeat number is low and you get sick later, does it progress more slowly?
Yeah.
I think that's true. Is that right, Dr. Dummett? Yes. So the earlier you get it in general, the faster things will happen. And if you are one of the lucky people that don't get sick until later in life, then things will move more slowly.
Actually, lucky people don't have a mutation at all. Other questions? Science questions? Dr. Gutman?
Let's pretend Ed was here. We would ask a question about biomarkers and what's new and exciting with biomarkers.
So biomarkers. Raise your hand if you have no idea what a biomarker is. Good. A biomarker is just like a lab test that we can do that will tell us about something that's happening in something in the body, right? So if you get your blood pressure measured, I'm trying to be a real doctor, it's embarrassing. That can tell you about how your heart is working, maybe, is that good? The point is, there's tests that doctors can do to like test and to track, say, the progression of a disease, which is one kind of biomarker. And so, for example, using an MRI scanner to look at people's brains, we can see changes in the shape of the brain as time progresses in people that have the HD mutation. That's one kind of biomarker. More recently, there have been some based on spinal fluid measurements or even blood measurements of different proteins. So one of them, for example, a protein called neurofilament, which is released from neurons when they get sick. So neuron cells in your brain, the ones that we want to try and keep alive in HD, as they get sick, like parts of their machinery kind of fall out, like they're getting kind of like garbage is kind of spewing out, and it actually ends up in your bloodstream, some of it, and you can measure those. And so as people, not just with HD, but lots of brain diseases, as they get sick, that you see that trash accumulating in the blood as time goes on. And Dr. White was part of a study, a lot of studies that happened recently on one of these, a particular neural protein called neurofilament, and you can measure it in the blood and it tracks disease progression. So the idea is, if we come up with, say, a lowering drug that makes HD better, and we see that it also makes these blood measurements better, then as we go forward with additional trials and new stuff, you might not have to wait so long and like look at people's HD symptoms. You might be able to give them a drug and see if you can make these measurements get better, and then say, okay, yeah, that's enough. We can get that drug approved. Something similar happens in HIV, right? So the first HIV drugs, they looked at whether people died or not, because there was no option. That was the only thing they had to compare to. Once HIV drugs were approved and they had lab measurements of viral loads, for example, you could get a new HIV drug based on whether you made their viral load go down, not just whether they lived or died. So there's hope that there could be a progression where we could use these markers to run trials faster and use them as endpoints. Does that capture everything?
That's it.
You want to talk?
What's happened in some other areas, for instance, Alzheimer's and other conditions that have protein use this as a marker for how the progression of the condition is. So there's work being done on mutant Huntington's protein PET imaging in Huntington's disease. And this is going into humans within the next 6 months in Sweden. There's a lot of work that CHDI is funded on this. So theoretically, in a couple of years from now, we may be having people go not just for MRIs with these PET images and use that as a measuring stick. Right now, we can say this is fantastic. The IONIS study showed a lowering of mutant Huntington's protein concentration in the spinal fluid, but we don't know where that's coming from in the brain. This will be brain regionally specific. The hotspots in the areas of the brain that are affected by Huntington's, that's where we want those things to get better. It may not be so relevant in other areas, so we can look at specific brain regions and see potentially if those are getting better with these agents. So that would be a really cool thing to happen if we could send people for a PET scan and use that. And that would be the segue into the pre-symptomatic individuals.
There's a question there.
Hi, yes, this has to do with the GWAS study. Just wondering whether or not, particularly with the group that were the late onset results, whether or not the study included, were there any environmental, dietary, or lifestyle aspects that might have contributed to a later onset? And I guess the second part of the question is, do you have any, does it matter, I guess, whether or not somebody lives a healthier lifestyle in terms of whether or not they get earlier or later onset?
So the original GWAS study just looked at the DNA sequences. They didn't have the information attached to it of, what was that person, did they go to McDonald's all the time or did they lead a healthy lifestyle? So the original, this information that we have is strictly just looking at the DNA. Having said that, GWAS isn't the only huge, large-scale study we have anymore. Now we have Enroll HD. So does everyone know what Enroll HD is? Put up your hand if you've never heard of Enroll. Okay, good. So most people have heard of it. So it's a huge observational study that is just looking at once a year, you go, you get your measurements done. They're looking at brain function, they're looking at movement, they're looking at, they take down what medications you're taking, and things about your lifestyle. I think they ask you about alcohol, drug use, these kinds of things. So now we're in the position to ask about how those environmental things affect. We don't know right now, but I can tell you that in general, leading a healthy lifestyle is never going to hurt. We should all, be thinking about staying active, eating healthy food, like a variety of foods and not too much processed foods, limiting our alcohol intake, no smoking. What else?
All the things you know you're supposed to do.
Because you hung out at the bar with me last night. Don't do what we did.
Yeah.
Take care of your brains. Yeah. Okay. Other questions?
Have there been any updates on looking at the role of stem cells in potential treatment for HD?
What do you think about stem cells?
So the question was about updates about stem cells in HD. So does everybody raise your hand if you don't know what stem cells are? Okay. Right. So stem cells are the cells that can become any other kind of cell in the body, and there's like an obvious, attraction to the idea that like if cells are dying in the HD brain, maybe we could replace them. There was some excitement about using stem cells as an actual delivery technology, for example, of something called mesenchymal stem cells to deliver trophic factors to the brain. As far as I know, that study has been halted and it's not going on anymore. It's the last thing I heard about it. It's tricky, right? It's hard enough to get a normal drug in the brain, just like a little small molecule. Putting like a living cell in a brain is complicated, said Dr. Carroll, right? Because it's still a cell, it's still going to go around and grow. And so I think, and results from other transplantation studies, and for example, in Parkinson's field, have been not very exciting, and it's tricky. So may it happen someday? Yes. Is there anything that I'm excited about in the medium term? No. Lots of lab work though happening in stem cells, which is amazing. So more recently, it's been possible to take, so the stem cells used to be controversial because they were so-called embryonic stem cells, right? You had to take them from an embryo, and it's controversial for lots of reasons. Years ago, not many years ago now, it was discovered that you could take skin cells from somebody, or any cells really, but say skin cells, and you can zap them with a couple genes, and they turn into stem cells. So because we turned them in, they're called induced pluripotent stem cells. And so basically now we're in this era where we can have stem cells for people like HD patients and controls, and it's an amazing research tool because you can turn them into neurons. So you can make like real human brain cells in the lab from HD patients and from their siblings that don't have HD and study them. It's an incredible tool for learning about what happens to cells that have a mutant HD gene. So that's like on the lab side, it's like a revolution. It's incredible things happening. I never thought we'd be able to study real human neurons in the lab, but now it's like routine, which is weird. Did that answer your question? No. Other questions? I told the YPad that I'm working on my awkward silence. I'm just going to stare at you guys until you ask another question.
We always tend to focus on the cure. I'm just wondering if you have any other updates on research that's been going on for some of the symptoms. I remember at a conference a few years ago, it was a married couple that were scientists that had used this thing where they went to every drug that already existed, and then they were pursuing a couple of them for treatment for some of the symptoms.
Yeah, I mean, to date, basically every trial that's ever been run in HD has been looking at symptoms. Often movement, not always. And fundamentally, that's kind of what we're left looking at. There's been some disappointments this year. There's been a few trials in the last year and a bit that haven't worked that were looking at symptoms. So the Liquinimod trial, the Legato HD trial recently stopped, for example. I encourage YPad kids to think about this. Sorry, kids, I'm old. The youth of YPad to think about this. Don't think of this as failure, right? Like there was a good reason that to think this drug might make symptoms of HD, in that case, movement symptoms better. And so it was tested. It doesn't work. Now we know that. Move on, right? That's not a failure. That's accurately answering a question. And so a few of those answers this year have come back. Last year and a bit have come back negative, which is too bad. But all of the Huntington Maiuri and other trials are looking at Huntington symptoms as well. But nothing novel besides that on the horizon that I know of. Awkward silence.
I have another question. Actually, a two-part question, so two different topics. One is, my husband was on the CR16 study that they ended abruptly and took the drugs from us, and we had a lovely month before Christmas. I say with a little bit of humor. So we had heard that there was a possibility that it was coming within the first quarter of 2018 to come back on compassionate use basis, and it's not back here yet. So do you know if it's, they're going to be bringing that back?
Does anybody, real doctors know?
I don't know of any efforts.
It's not clear that anyone's trying to at this point.
Okay. Because we found that it was holding Bruce back from his symptoms. He wasn't replying. So we really found it effective, so we were quite upset that it was taken away from us so abruptly. And for no reason, there was no explanation why it ended. The second question is how to, because I know dopamine is a happy drug, natural drug. And so my husband and I, our theme is be happy. So even though we're in, it could be in stressful situations or happy situations, it's be happy. And I'll tell you, that helps.
One of the reasons I started studying neuroscience was PET scans, the kind of scan Dr. Carroll was talking about, showing changes in dopamine in people. And in one case, when they just participated in a clinical trial, and you can see the happy chemical, like, this is science, this is not, you can watch dopamine flood the brain of someone who is participating in a trial, even if they get placebo, which is weird. And so to answer your first question about access to the drug, as far as I know, the drug didn't work. Not saying it didn't work for him, just saying it didn't work on a population level. And so if nobody's going to do another trial or try to market it, it's unlikely it's going to be available.
I just have one thing to add about. Oh, go ahead. No, you go first. Is it about the ACR16? Then you go first, because mine's about your second.
So dopamine may be developed, and if we're tested for some other disorders, as far as I know, there isn't any immediate plans to retest HD.
I just wanted to comment on your second it's, this is the part where I get all personal. So I know a lot of you know this, but some of you may not know that I also come from an HD family. And so I've had to deal with a lot of the things that you have to deal with. And I think that this strategy, this Be Happy strategy, it's not just some, fanciful idea. It's, we're all in this situation that we cannot change. And so it's either, this is the part where I also talk about my personal life. I've been taking Kung Fu. And the martial arts, that's another thing that they really emphasize is how to accept situations and how to think about situations and how to perceive situations and do what you can. And if you can't do anything and you have to accept the situation, it's how you perceive it that is going to make you miserable or be able to lead your life. And so I know that wasn't a very scientific answer, but for what it's worth.
Give me the mic, baby. I say don't do that. And don't do Kung Fu, it's bad for your brain. Do you wear a helmet?
I haven't started sparring yet.
Wear a helmet.
Wear a helmet, yeah.
Yeah, another question in here.
Is one of the blind spots in HD research the fact that there may be people out there with the HD mutation and they never get sick?
We talked about this yesterday because I said, well, there's nobody with a mutation that's not sick, but of course we wouldn't know.
Because they would never gone to the doctor.
I also, just as a technical thing, because of the nature of the HD mutation, this long CAG expansion, the way that like some of these big genetic studies that are happening, like this GWAS and Huntington's and other studies for other diseases where you might find those people, you can't see those long CAG repeats. So technically, we haven't been able to build the kind of data to look for the unicorns, the people who have a long expansion and don't get sick. But Dr. Levitt might have something more specific.
There have not, so what you're talking about is sort of population-based screening. There have not been a lot of population-based screening, but the Hayden group has looked at reasonable numbers. I think it's up to close to 10,000. And there's no question that there are repeats in the 36 to 39 range that exist in the population at a higher frequency than we would have predicted from all of our studies. And there's no question that when you base all of your studies on the DNA that we have at HD clinics, it's biased towards people who have presented. So it is biased towards people who would be on the earlier end of the spectrum. So there's no question that in the general population there is more HD than we believe. And actually this is really important for all of us to understand that the prevalence, the number of HD cases in the population is increasing. It's a disorder that's becoming more and more frequent because the population is getting older and older. So more people are living long enough to develop symptoms with these low repeats. So it is a rare disorder, but it's much more frequent than you may read in certainly in older textbooks. And it's increasing in frequency all the time.
I think it's because people with long CAG repeats are more attractive and smarter. It's just my pet theory.
That is definitely here.
Thank you. I get affirmations from the front row. Dr. Cutman is shaking his head, but I'm ignoring it. Go, Dr. McCrellins.
I want to talk about exercise.
You can, I'm not going to.
So somebody asked a question before about lifestyle, and there was actually a study from Australia that was very interesting. They asked people, what was their exercise activity and activity level like earlier in life before they developed Huntington's. And I don't remember what I did when I was 10, but this study was the best so far to say that if you exercise early in life, if you're more active, you get Huntington's later. So that's an interesting thing. We know in experimental animal models, if you have, and I talk to patients about this all the time, or people that have inherited the CAG expansion, in a mouse, if you have a mice with expanded CAG repeat that's being inserted, a transgenic mouse, and you have some of the mice in that litter exercise, and mice exercise by running around treadmills all night, versus if they don't have a treadmill, the ones that have the treadmill access actually get the Huntington later, from what I understand, and that was sorted out a number of years ago. There were experiments getting different answers, and one of the things was you have to treat all the mice normally, but it seems that exercise is a good thing. And this is a common theme in many of the neurodegenerative diseases. So there are NIH grants going on right now in Alzheimer's disease, or at least mild cognitive dysfunction, to see if you get the study actually paid for personal trainers coming 3 days a week to their homes to see if they exercise, and would they get the transition from this mild cognitive impairment into Alzheimer's less frequent. So that's interesting. In Parkinson's it's interesting, and we think it's interesting in Huntington's as well. So there are studies going on in Wales. There's a group of HD physiotherapists who are leading a large study looking at exercise and looking at the outcomes. So that may be something that's going to come forward in the next while. So if you ask yourself the question, if you're at risk, what should you do? We don't know right now. There's nothing proven, but exercise might be something you want to do.
I'll try to explain. You guys are smart scientists, so you'll figure it out, I'm sure. The difference between juvenile and adult onset, like if someone gets it, say at age 26 or later in their 20s, but they had cognitive symptoms earlier, like which is that, juvenile or adult, or maybe it's too hard to say, but and why are the symptoms different? It sounds different.
This is my personal opinion, not a real doctor. I don't love this idea of diagnosis, right? Of this concept that there's like a sudden change and all, because you're all from HD families, you know. There were changes, they were subtle, then they were less subtle, and then they were definitive, right? So what you're describing could be perfectly true, that those cognitive changes could have definitely been part of the disease process, but just not sufficiently severe enough that they were obviously HD, which is what you need to have a diagnosis. So I think that's, to answer your question, I think it's totally reasonable that could have been part of the disease. And then you said that the symptoms for juvenile HD are sometimes different. And again, not a real doctor, but from what I've read, that's definitely true. And then the really long CHA repeat that you need to get juvenile HD affects other kinds of cells in the brain and even other parts of the brain. So some kids with juvenile HD even get seizures. And so it can look different because maybe more parts of the brain are affected or different parts of the brain are affected because of the really, really long expansion. I was nervous answering a medical question with these neurologists in the front row. Someone asked me about a mouse.
Okay, I do have a sort of research-focused question. I just wonder if you could talk a little bit about the advantages that Huntington's has as a monogenetic disease in terms of research and where we're going, what our prospects are.
Huge. So HD is the model. HD is, I've talked to HD families so often, they're like, oh, everyone knows Alzheimer's, everyone knows Parkinson's, but no one knows HD. And that may be true, it's a rare disease, but I think we have such advantages from things like the Enroll HD study, from these biomarkers, because we can track people, because we know from conception who's going to get sick and who's not. And also, I don't know if people have been paying attention, but like, for example, in the Alzheimer's field, there has been expensive failure after expensive failure after expensive failure of drugs in the Alzheimer's field. And part of that is that maybe by the time we're trying to treat people with Alzheimer's, maybe it's kind of too late. And so in HD, we have the option of saying, okay, we can identify who's going to get sick, let's treat them earlier. And so I think a lot of people are focusing now on HD as almost a paradigm, like an example of how do you treat a disease when you can identify people ahead of time. My bet, if I had to put money on it, I don't have any money. If I had to put Dr. Gutman's money on it, or any of the other real doctors in the front row, I would say that I would bet that we'll have effective treatments for HD before there's disease-modifying treatments for those other more common neurodegenerative diseases.
And sorry, do you anticipate they might lead to treatment in the other neurodegenerative diseases as well?
So some treatments, like if there's things that are generally protective for brain cells, those might work in other diseases. We're getting into a funny/cool era now, which is that we're treating the underlying cause of HD, right? So with the Huntington lowering treatment, it's very unlikely any other disease is going to want to lower Huntington. So it's kind of good news, bad news. It's bad news because it means that these drugs won't be widely used in other diseases, but it's because they're very specific, and that's a good thing. These other targets, like the DNA repair genes, that might be a common feature of maybe not all, but maybe many other neurodegenerative diseases. So it's not a simple answer to your question. Real doctors.
Yeah, I would just say that this is a real reason to be studying Huntington disease. Aside from the fact that I'd love to help the patients that I see, is that it can serve as a springboard for these other much tougher, more complex disorders where not only can we not say who's going to get it beforehand, when they have an Alzheimer's disease study, they might not have only Alzheimer's patients in it. There are misdiagnoses, even Parkinson's. There's sometimes after the patient dies and there's an autopsy, they realize, well, that wasn't actually Alzheimer's, that was this other type of dementia or this mimic of Parkinson's. So they're trying to treat a disease where they can't even identify, even when people get sick, that this is definitely what they're trying to treat. But we do know that in Huntington disease. And the question about pathways that are common, well, if anyone was in my talk, there are a lot of common pathways. So even though targeting Huntington is not going to work for Alzheimer's, there are all the other things, the antioxidants, the inflammation, other things that protect neurons are pretty common among them, and what's happening at synapses is happening early in all of these. So if we find things in Huntington's which we can define more readily and be very clear about what we're treating, I think it could lead to, could translate. Finally, even lowering Huntington. It was first in man, first in man, anyway, to show that you could put an agent get the agent into the brain and change protein in the brain, at least as readout from spinal fluid. So that in itself, it helps us. If maybe they want to lower A-beta, the protein in Alzheimer's disease. Now they have a path forward because it's been tried before, and so maybe you can do it there.
That's exactly what I was going to say, that in HD, we've led the way with the first Ionis study. So I've been approached to do a study with Ionis, an Ionis molecule, in genetic Parkinson's. There's genetic Lou Gehrig's disease, there's genetic Alzheimer's. The programs are starting after the Huntington's lead. So this kind of technology of lowering RNA, or RNA silencing, or lowering proteins, is going to hit the road running. There are other, even rarer conditions called spinocerebellar ataxias that are going to be targeted with this kind of strategy. So Huntington's has led the way, and we know that it's possible. And it's really exciting times. So people with much rarer conditions that don't have any CHDIs behind them or Huntington societies are really going to get benefit from the experience that we're having.
And I would just add one more thing, which is that there's another reason I think that HD is going to be the leader in this, and that's that we have this special community that has stepped up in a huge way, right? So I don't know of any other diseases that have an observational study with 16,000 people in it. Are there? I don't think so. I don't think there's that, so the fact that everybody has stepped up and worked together is one of the reasons why HD is going to be the forerunner on this.
I'm just a little confused here when it says a 50-50 chance, like from one parent to the other. As a livestock producer who works with genetics, and in our family, I'm no math whiz, but we're at 50-50. My husband's mother's family, 4 to 5. One of those grandchildren, parental planning, had eggs harvested, sent to Detroit, 11 eggs harvested, 2 came back. I'm not, no math is, but our family's not 50.
Yeah, I know.
It's not dominant, like you have to, I've got to be a 2 genes, you're going for color, whatever. It's the same, but one is dominant.
So it's a hard math to understand. It always blows my brain because way to think about it is that it's 50-50 for each one of the siblings. So in my family, same thing. My grandfather, there were 4 siblings and all 4 of them got the gene. That's not 50-50. But you have to think of it more of like flipping a coin for each one. And if you flip a coin, you can easily get heads 4 times in a row, right? Like you know that can happen. And so it's not, I mean, it is unlikely that it's less likely. I better not start talking probabilities because my stats is horrible, but this is how it works. It's a flip the coin for each one. So sometimes you get 4 heads in a row, and that's just how it goes.
Yeah, it'd be better if there was 4 tails, but... yeah, okay, so other questions? Science questions? People in the back. Awkward silence. I'm fine with it. Yes. I got it. He had, you know, better options. He has a very large grant that he is in the final running for, and the UK is very old-fashioned or very like fancy in some ways, and so you have to go to London and like present yourself personally to get interviewed for a grant. So he could have come, but it would have cost him £2 million, so he decided not to come. I figured that was a decent excuse. Although he genuinely loves the HSC, because you guys are nice to him. And not really any other people in his life are.
We don't know.
See, we don't know yet. He's got to go wear special robes or something. Like, so I'm picturing like Hogwarts, basically, which I'm sure is correct. At the at the Hidden Memoir at the Vatican. Yes. Yeah. Of course, there was someone famous there, and then weird, Dr. Weil showed up. Strange. What are the chances? Yeah, in the back row.
I have a question in regards to some genetic.
I don't think the mic's on. Sorry to interrupt you. Better?
Yes.
Okay. So I have a question on some of the genetic tools from the 14,000, 10,000, 16,000. Have there been any tools from that to also count? Is there a higher autoimmune disease correlation with people that are affected by Huntington's, or are there any other anomalies such as resistance to cancer or anything else that can be in this area?
Yeah, I mean, one of the most fascinating things is this really weird but several times repeated observation from, this is a couple Scandinavian countries have been looked at where they have registries of like literally every person's health records, and so they don't just look at a sample, they look at the entire population, in this case of HD patients. And a repeated observation is that people who have the HD mutation have about half of the cancer that are found in other people, which is striking, and it's corrected for lifespan, because obviously people with HD tend to die earlier, but there's, you know, deal with that math and say like how many times per year do people get cancer that have HD mutation, and it's markedly lower in people with HD mutation. To the extent that I've often said in conversation with people, like if it wasn't for this whole unfortunate brain cell death side effect, like if there was a pill that would make you have half the cancer, everyone in the country would be taking this pill, right? There's something, it probably paints a picture about some interaction of the Huntington gene and these DNA repair pathways that Tam talked about is one explanation. There's a couple other explanations. So that one's been repeated a few times. I think the immune story is a little more complicated. I don't know of definitive large-scale studies, but now that we have the enrolled database, that's good. We're going to be able to do on a much bigger scale, much better sense of being able to take those things apart.
Metformin might give you first. So
basically, it's still early. So this kind of big, large-scale information about things like autoimmune disease, it will come. The data is there now. Now we need researchers to go in and mine it and figure out what's going on, and that is starting. So one example is one group of researchers looked through the information and they asked, okay, so there's, we have 16,000 people. Some of them are going to have diabetes, and so they're going to be taking metformin. And there was some indication in like animal models that metformin might be beneficial. So now we actually can go and ask, do people that take metformin, are their symptoms different? And they did actually find a difference. It was just for the cognitive, like for the brain function, but they found that people with HD who were on metformin their cognitive decline wasn't as quick. So these are the kinds of questions that we can start asking now.
We have time for a few more questions.
I'll ask this question because you wanted someone asking the best questions. So we know, like I've heard you say before, that there's the Huntington, the gene is in every creature from Vita straight up to us. Is Huntington, like the repeat rate, as unstable in other creatures as it is for humans?
Yeah, so this is kind of really a fascinating question of like, why do we have these long repeats at all if it seems, as it is obviously the case, they can like expand and cause diseases like HD. So one curious fact is that sort of, if you look across evolution and look at animals that have larger, more complex brains, they tend to have longer CAG repeats. So sea urchins, right, like spiny sea urchins have a Huntington gene, and they have like one CAG repeat. Well, it's not a repeat, it's just one. Fish have like 4 CAG repeats. Mice that I work on have 7 CAG repeats. Primates have, non-human primates have lower CAGs than we do, and we have around, humans that don't have HD have around 17 CAGs. So there's something about longer lifespan or bigger brain. I mean, there's a lot of things that are correlated with that, but for some reason that CAG repeat in Huntington gets longer as you go along. To get Huntington to be unstable, like it has to be to cause longer repeats, you need something longer than 7. So mice, if we look at mouse Huntington CAG sizes, and they like never change. So it's like it's not long enough to be unstable to lead to this kind of stuttery thing that leads to HD. So as far as we know, humans or maybe potentially other primates that we've never seen would be the only ones that could have something like HD by having the CAG get longer. So that's like a really fascinating basic science question that we really don't understand. Like why is that CAG repeat getting longer across evolution? I'm not sure.
So it's break right now. And thank you all for coming, and give a round of applause.